If this is your first time joining us, welcome. If you've been here for a while, welcome back. Today, we'll be starting to explore the ideas of modern physics. Topic 7 of AP Physics 2, for those of you keeping score at home, we'll be talking about topic 7.1, that's systems and fundamental forces, and talking a little bit about wave functions and probability, but mostly we'll be focusing on atomic theory and what atoms are up to. So as always, we're going to start by going over our agenda really quickly. First of all, there's going to be a lesson overview. We'll talk about what we'll do throughout the lesson. And then we'll do our daily warm-up. We'll pick up right where we left off yesterday and get your brains started thinking about atomic physics. Then we'll discuss what you need to know, all the key points that we're going to learn today. After we go through all that material, we'll do some guided practice. We'll work through some AP test questions and really get you making sure that you picked up what you were supposed to learn. We'll talk about the lesson, we'll summarize it, we'll debrief, ask you some questions, and then we'll finish with some AP exam practice, which we'll answer tomorrow. So once again, I'm Joe Mancino. I teach at Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton. I teach at Reedy High School in Frisco, Texas.
And here comes a lesson overview.
All right, we're going to start with fundamental particles, talking about protons, neutrons, and electrons. And we'll also dive into quarks just a little bit.
We're going to talk about the Bohr model of the atom, the idea that electrons have discrete energy levels, and we can treat electrons like point particles that are moving in circular orbits.
After the Bohr model, we'll talk about the modern theory of the atom, including wave functions for an electron or particle, and graphing and calculating wave functions.
Then we'll talk about emission and absorption spectra. We'll look at representing the different energy levels in the atom and how you can determine those from the emission spectrum of the atom, and how to see that when you look at an emission or an absorption spectrum, you are looking at something unique to that element.
You should already know the basic particles that make up an atom, and remember from the previous lessons, frequency, wavelength, and velocity for waves and light.
So the skills that you'll be using today are using representations and models to solve problems. You'll be making claims and predictions about natural phenomena. You'll be connecting concepts across topics.
And by the end of the lesson, you should be able to calculate the mass of an atom, determine the wavelength of spectra, and interpret wave function graphs.
Okay, so that's a lot of stuff to do today. Another jam-packed day of AP Physics. So here comes the warm-up problem, right where we left off yesterday. We had a boat and it was leaking oil. And looking at that oil slick, there's a spot that looks like extra green. So I hope you took a screenshot about this yesterday. I hope you were thinking about it a little bit. First off, do we treat this like a film or like a coating? Well, if you look closely, it says N equals 1.5 for the oil. Well, I know N of air is 1 and N of the water is just 1.3. So that N equals 1.5 is more than either air or water. That means that the oil is acting like a thin film, not a coating. So we think about the mathematics of thin films. Now, if we were going to answer this numerically, we would say, oh, the minimum thickness is 1/4 of the wavelength of the light in the oil. And yeah, we could figure that out, okay? I know. But this question is about how it works, not numerically what it is. So the idea is that light reflecting off the air-oil surface undergoes a phase change, and light reflecting off the oil-water surface does not undergo a phase change. But when those reflected beams of light combine in the eye of the beholder, the green wavelengths, because of the geometry of the oil, because of the thickness of it, those green wavelengths add up. The crests meet the crest, the troughs meet the troughs. It's a brighter wave. It's extra green. Now, certainly other colors are following the same physics, but the result is that wavelengths that aren't that Goldilocks wavelength, they don't add up the same way. They may interfere destructively, or they may just not add up well at all, to the point where, yeah, you'll see them, but you won't see them as amplified as you see the green.
All right, so here is your warm-up question. Which of these two phenomena involving light can be explained with a particle model? Notice particle is bolded. We know that in the last couple of lessons, we talked about light acting as a particle, acting as a wave, so on and so forth. And you should be able to pick out between these four answers which ones are significant in talking about light being a wave. So the two that we talked about last time that identify that light is acting as a wave is diffraction and thin film interference, just like the question that we just went over for the AP exam practice. So the answer to this one is not the ones that act as a wave. It's the photoelectric effect and atomic emission. And we know that you probably haven't heard those terms before, but if you have, this is indicative of the particle model. So moving on to
Sounds like a little bit of foreshadowing.
It does. So in today's lesson, what you need to know is what an atom is made of. Electrons are fundamental particles. Protons and neutrons are composed of these fundamental particles. The mass number and the atomic number, and kind of what the difference is between the two, and how one atomic mass unit is roughly the mass of a proton. Once we get to atomic theory, we'll talk about observations in the late 19th and early 20th century that challenged how classical physics described matter. And the modern idea of the atom explains these observations better than classical physics did. So we'll start with classical and move into what we call modern. And electron energy levels. So with electron energy levels, atoms can emit and absorb energy only in discrete allowed amounts. And we'll use that word discrete several times throughout the lessons today. Last but not least, energy level diagrams help us predict which photons interact with an atom.
But first, we need to make sure that we have a really good definition, a good understanding of what an atom is. Presumably, these students have taken chemistry. Mr. Eaton, what do they need to know about atoms?
So we need to start off with the fact that atoms are just stable and electrically neutral. And atoms have chemical properties that allow them to combine with other atoms. So bonding.
Now, chemistry talked a lot about electrons. I remember outer shell electrons and valence electrons. Nuclear physics doesn't sound like it talks about the outside of an atom. Nuclear physics is all about the middle of an atom, the nucleus of an atom.
So atoms can emit and absorb electromagnetic radiation with discrete energy and momentum, very specific energy and momentum. Most of an atom's mass, however, is associated with the positive charge, aka protons.
So matter is composed of fundamental particles. You've probably learned about electrons, protons, and neutrons making up atoms. I think that you're probably really familiar with the symbols for them, electrons carrying a negative charge. I always give it on my board an E with a little negative sign. Protons get a P and neutrons get an N, and those are the abbreviations that I'm used to. The mass of each one, I think that you're pretty comfortable with. Electrons are significantly lighter than either protons or neutrons. Electrons carry negative charge, protons positive charge. Protons and neutrons have the idea of size. Now, that's not a lot of size. 3 femtometers is really small. Electrons, they are so small that the idea of size does not work really well for electrons. They're the smallest bits of matter, but they're so small that the word size is kind of funny. Protons and neutrons have about the same mass, approximately, you can see it right there, but it's roughly 1,840 times the mass of an electron. That's why electrons are the mobile charge carriers. They're just so much lighter. Well, today we're focusing a lot on electrons within an atom and those nucleons within a nucleus.
All right, to add to your list of proton, neutron, electron, today we're going to talk about electrons, neutrinos, photons, and quarks, and how they're examples of fundamental particles.
What do you mean by fundamental particles?
Well, fundamental particles are what make up those protons, neutrons, electrons.
Oh,
So
so,
neutrons and protons are composed of what we call quarks.
okay, so fundamental particles make up other particles, but fundamental particles can't be broken down into smaller pieces. Wait, neutrons
Correct.
and protons are not fundamental particles.
Hmm.
Quarks, the building blocks of neutrons and protons, they have electric charges which are fractions of the elementary charge of the electron. Now, I know what we taught you in Physics 1, and that's okay. Protons, they absolutely have they have exactly a charge equal to the fundamental charge. Electrons have a quantity of charge equal to the fundamental charge. Quarks come in different flavors. I know it's not a great word, but that's what it is. We had to call them something. There are up quarks and down quarks, charmed quarks and strange quarks, top quarks, bottom quarks. You don't even have to know that. What you should know is that quarks have fractional charge. Half of them, they have a charge of plus 2/3, and the other half of the quarks, they have a charge of negative 1/3. Super weird. Protons are composed of 2 ups and a down. It looks like this. And if you add those up, you get to plus 1. Neutrons are composed of 2 downs and an up. And if you add those quarks up, well, you get to no charge. You get to 0 charge. So I've thrown around the word nucleon today. What did I mean by that, Mr. Eden?
So a nucleon is just the particles that are inside the nucleus, the region that we call the nucleus. And it's either a proton or a neutron, clearly not electrons because electrons are not in the nucleus. And the atomic number of an element is equal to the number of protons. It's kind of like the identifier of the element. And so those protons obviously are in the nucleus of the element, and that's how we name elements. The mass number, though, is equal to the total number of nucleons, again, the particles that are in the nucleus, so protons plus neutrons. So atomic number, protons, mass number, protons plus neutrons. In our first example that you see, we have boron. And just looking at boron, how many protons do you see there? Looks like it's the purple dots, and I see 5. So boron has an atomic number of 5. However, the mass number is going to be the protons plus the neutrons. So behind the purple dots, you can see the yellow spheres. I see 1, 2, 3, 4, 5, 6. So 6 plus 5 gives me 11 for the mass number. So
Let's take a look at this. I know, no offense, chemistry teachers, but my chemistry teacher always said, chemists are lazy. We never like to write anything out. So they abbreviate an element by taking typically the first letter or two, or maybe the first letter or two in their Greek equivalent or a historical name for the element. But that doesn't matter because the letter does not identify the element. The letter is arbitrary. We named it maybe after somebody. But like Mr. Eaton said, the atomic number is what identifies the element. And you're right, there's 1, 2, 3, 4, 5 protons there. But do you remember what the nucleon number was, the mass number was? There's 11 of those. All of those add up in the nucleon number. A convenient way of describing an element is by giving its mass number and its atomic number, along with its chemical symbol. So you may have seen this presented in a chemistry class with the A number being the total number of nucleons and the Z number being the atomic number, that one that identifies what the element is. So here we have beryllium, a nucleus of beryllium with 4 protons, but 9 total nucleons. From that, you can determine how many neutrons there are. I'm not going to make you do 9 minus 4, but that's how you do it. So that was one possible version of that atom. But for many elements, there are different ways for nucleons to organize. Those different versions of the element are called isotopes. Iso means the same, and topes mean, I don't know what topes mean, but iso means it's the same element, but a different version, a different number of neutrons. So here we see two versions of helium. On the bottom left is a helium with just one neutron. That's 2 protons plus 1 neutron. That makes helium-3. On the bottom right of your screen, you see helium-4, 2 protons, 2 neutrons. Helium-4 shows up again later. So the total number of protons determines the element. The total number of nucleons determines which isotope of the element that it is. Mr. Eden, let's hear about the weird units we're going to be using.
These are kind of funny sounding units, but they're useful for us because the things that we're talking about are very, very, very small things, and we need very small units in order to do so. So for wavelengths, which is a distance, we'll be using nanometers, which is meters to the times 10 to the power of -9, and electron volts for energy instead of joules, and atomic mass units for mass instead of kilograms. Because really, if we wrote all those numbers out in terms of kilograms or joules or meters, we would have a decimal point and so many zeros, it's just super difficult to write. So instead we use nanometers, electron volts, and atomic mass units.
So we should probably define atomic mass units. 1 AMU, or 1 U, 1 atomic mass unit, is defined as 1/12 the mass of carbon-12. It's approximately the mass of a proton or a neutron, but it's not quite equal to either. And we'll talk about why that is later. A free proton has more mass than 1 AMU. A free neutron has more mass than 1 AMU. Hydrogen has more mass than 1 AMU. You're probably going to want to screenshot that. So here's boron again. The average atomic mass of boron is, boron 11 is 11.009305 Us. I'm not going to make you calculate what the atomic mass of a boron nucleus is. But here's the idea. If you screenshotted the last screen, then you can figure out the mass of all the electrons in boron. That means you can figure out what's left over to be the nucleus. So the total mass of boron is the mass of its nucleus plus its electrons, rearranged for the mass of the nucleus. Do the math out. The mass of a boron nucleus is about 11.00656 Us, or 1.83 times 10 to the -26 kilograms. So speaking of people named Joe, here's J.J. Thomson. That's Joseph John Thomson. He discovered that electrons were discrete parts of an atom. They were separable from atoms. And he did that by doing something you may have studied when you studied magnetism. J.J. Thomson sent a beam of these negatively charged particles through a magnetic field, steered them with a magnetic field, accelerated them the other way with an electric field, and balanced out electric and magnetic fields until, by looking at the path of the electron, he was able to determine its charge to mass ratio, to determine that there were these very small, light negative charges inside of atoms. You may have seen an apparatus like this one. Anyhow, J.J. Thomson said, wait a minute, we've been thinking that atoms were electrically neutral, but indistinguishable, unbreakable. That's what the word atoms means. It means indivisible. Well, Thomson had discovered that there were divisible negative parts inside of this atom. So his idea was there are lots of little negative particles floating around inside of an otherwise positively charged mass of an atom. So in J.J. Thomson's mind, he pictured this, and on your screen you can see an image of kind of what it would look like if there were some negative particles floating around inside of some jello-looking positive goo. Now, he thought it looked like plum pudding. Pudding, of course, just meaning dessert. Delicious. So Ernest Rutherford set out to do an experiment to prove J.J. Thomson's model. Now, Rutherford's idea was that he could send particles through a very thin film of gold. And he could send positive particles in there that would be slightly deflected by the negative charges, the tiny negative charges inside of those gold atoms. Now, we call it the Rutherford experiment because Rutherford was the primary experimenter, but Rutherford had two very famous grad students working on the experiments, which would probably be called the Rutherford Marsden Geiger experiments. And yes, that Geiger counter, it's Hans Geiger. So their idea was that they would send a stream of positive particles into that thin piece of gold that you see right in the center of your screen. Now, they would send very small alpha particles. That's a helium-4 nucleus. There it is again. They would send them through the gold foil. And most of the particles would go through the gold foil. Alpha particles very small, gold particles very large. There should be room. So the idea was they would go through, but a few of those alpha particles would be slightly deflected. Some would go that way, some would go that way. So there would be some deflection, some angles that they went through. And the idea was that by looking at the distribution of how the alpha particles distributed, they'd be able to figure out the concentration, they'd be able to figure out some properties about atoms. And that was great for maybe 7,999 out of 8,000 trials. But every once in a while, there was a ricochet. Now that's weird. Sending tiny particles through a bunch of big particles shouldn't be a problem. They shouldn't ricochet. So pretty quickly, Rutherford and his team realized that the interesting part of this experiment is not on the right side. The interesting part's on the left side. It's the ricochets. They proposed this.
That an atom is mostly empty space with a very dense nucleus of concentrated positive charge. That's where the ricochets were coming from. The alpha particles were bouncing off of the nucleus almost backwards. But again, that's only 1 in 8,000 trials. And the other thing that they proposed was that electrons must orbit at a distance in order to avoid electrostatic attraction to the nucleus. So electrons are attracted to the nucleus. Why? Because the nucleus contains the positive charge, and negative and positive is clearly attracted to each other. So through this experiment, the empty space determined that electrons must travel far away from the nucleus. And there's obviously a very dense nucleus with a positive charge at the middle.
So up to this point in history, physics thought we had a lot of stuff figured out. We had the classical model of the atom, and we had ideas about how charged particles work. One of the discoveries that was made when we were able to separate, we were able to charge particles and accelerate them using fields, we knew that a charged particle accelerated by a centripetal force should slowly radiate energy. And that energy loss should decrease the charge's velocity, sending the electron crashing into the nucleus. That was a prediction of classical physics, that this should have happened. But it doesn't happen. So another not so famous Joe, Joseph Larmor, who was doing research on particles moving through the luminiferous ether, remember, we're still trying to solve the ether business at this point in history, discovered that, and don't write this down, students, you know who you are. Joseph Larmor discovered that the rate at which a charge would lose energy as it traveled in a circular path depended on the charge of the particle and its acceleration. So accelerating a charged particle should have it radiate energy. It should do this. Particles, electrons orbiting nuclei, they should collide. The electron should lose energy. But you see, it doesn't happen. The instantaneous collapse of all atoms and the destruction of all matter doesn't happen. And classical physics couldn't explain why it doesn't happen. And if there's one thing classical physics is supposed to be good at, that's explaining why. And even if classical physics can't figure out the why, it should at least be able to make good predictions. So the problem is in the idea of classical physics. Classical physics is defined as a certain time period. It's really based on the precision of our tools. Classical physics had done everything that it could with the tools that were available, but when it started making predictions that weren't matched by experiment, that's when there's a shift from classical physics to what we call modern physics. Now, I know the word modern is a little bit weird. It's been 115 years since modern physics started. So 115 years ago doesn't feel very modern, but in the grand scheme of human scientific history, 150 years is still pretty recent.
Which most of it started with the Bohr model. So the Bohr model started with an observation of atomic spectra, which made it obvious that atoms can absorb or emit energy, but it's only in discrete amounts, very well-defined amounts of energy. So in 1913, Niels Bohr said that the classical theory could not explain Rutherford's atom. And instead, he intended an explanation that says an atom can only have a certain set of orbits, not others. So there's really no middle ground. It's either one orbit or the second orbit or somewhere past that. An atom, though, has definite energy levels analogous to standing waves, very similar to what we talked about in Physics 1 with waves inside pipes and waves on strings.
So here is physicist Niels Bohr, aging gracefully, doing physics. In the Bohr model of the atom, the nucleus is a dense positive center, and around that dense positive center orbit electrons in different shells you probably learned about in chemistry. But the Bohr model has electrons as discrete particles orbiting a central positive nucleus, something like that. So in Bohr's model of the atom, we see that there is a nucleus that contains protons and neutrons, and surrounding those are electrons. And I want to zoom in really quickly to just the nucleus itself. Those positive particles, those protons, they have positive charge. They're still doing Coulomb's law. Remember, KQ1, Q2 over R squared, that's a really, really, really small r. And when the radius in the Coulomb's law equation is that small, there are incredible electrostatic forces being exerted between those positive charges. But the atom still doesn't crack apart because of that. There's a force even stronger than Coulomb repulsion, and it's called the strong force, which is really the most boring name for a force. Listen, if you ever get to name the best and strongest version of something, do a better job than physics did. The strongest force in all of nature, it's called the strong force. But that's the force that binds protons together in a nucleus and overcomes Coulomb repulsion.
Brings us to the modern theory of an atom, which really states that the model of an electron as a point particle moving in a circular orbit is kind of outdated. We now have what we call the quantum model, which presents the fact that the location of the electron is a probability distribution, a kind of a cloud around the nucleus. So there's not just little orbits like you see in like a planetary system. So additional quantum numbers have been added to describe that shape, orientation, and magnetic spin of the electron. And the Pauli exclusion principle showed that no two electrons in an atom can exist in the exact same state. So this brings us to the wave function. The wave function describes the probability of where you can find an electron at certain energy levels. So you'll need to know how to interpret a psi versus x graph. And the location where psi squared has the greatest amplitude is the location, this is on the graph, is location with the greatest probability of locating the electron. We'll show you an example here on the next slide. So here's a graph of psi versus x. And remember that psi squared is the probability, aka if I take a negative number and square it, I get a positive number. So in looking at the graph, psi on the y-axis has a maximum amplitude of +1 and a maximum negative amplitude of -3. So if you were just to look at this without really doing a ton of thinking, at what position do you think is the greatest probability of finding the electron? I'll give you just a second to think about that. Okay, and you'll notice that the amplitude is greatest at 2 meters, which is right in the center of the graph. So regardless of whether or not it's negative or positive, that's still the greatest probability because we typically talk about psi squared.
So at no point in your study of AP Physics 2 will you have to determine the psi of x function, the wave function for finding an electron in an atom. If you decide to major in physics and you study quantum physics, you'll actually have a blast finding wave functions and figuring out where electrons are going to be. But it's a lot beyond the scope of AP Physics 2. Your job as a smart AP Physics student is to appreciate the fact that ideas like location, for something as small as an electron, well, those ideas don't have the same physical meaning as the location of, say, a bowling ball. For electron, the idea of location is defined by a probability function. It's a series of overlapping maybe. So you won't have to do the calculation. The math is three-dimensional. It tells us about the shapes of electron energy levels. And if you've seen diagrams of electron waveforms, probably in a chemistry textbook, those are consequences of calculating the wave function of an electron. But we'll be talking about Bohr's planetary model. It's a really good model. It's a pragmatic model. It makes really good predictions, and it gets us most of the way that we need to go. And that's what makes a scientific model worthwhile. So in Bohr's planetary model, the electrons are moving in circular orbits around a positive nucleus, and Coulomb attraction, that KQ1, Q2 over R squared from a couple units back, that provides the centripetal force. So KQ1, Q2 over R squared equals mv squared over R. We do a little bit of math, and we find that the radius depends on the charge of an electron and its mass, and there's a relationship between radius and speed.
All right, that's enough about models, but we do know a couple of things for sure. We know that all objects continually emit and absorb electromagnetic radiation. So not just electrons, but we're going to talk about electrons here. And here's a new term. It's the emission spectrum of a material. And what an emission spectrum does is it shows the colors given off the material when it's burned, or in the case of a gas, electricity is passed through it, kind of like a long fluorescent tube, or you may have seen gas emission tubes in your chemistry class. And if you wore those special diffraction glasses, I think this is what you would see, right, Mr. Mancino?
Oh, absolutely. And some of you may have done this with those emission spectrum tubes. If you've looked at them through a spectrometer, you've seen these characteristic colors. On the top is hydrogen, followed by sodium, helium, neon, and mercury. When electricity is passed through those gases, they burn only those colors, not a continuous spectrum of colors like classical physics says that they should.
In contrast to emission spectra, there's also what we call the absorption spectrum. And it's related to the emission spectrum that we just talked about, but it only shows what colors of light are absorbed by the material. It's just the complete opposite. So instead of bright lines on a kind of a black bar where you saw them separated by a certain distance indicating their wavelength and their frequency, this is going to be more of almost a continuous looking spectrum, but it has missing pieces inside of it. And each one of those missing pieces where you see kind of a black line across the spectrum, that's where the frequency is actually absorbed by the electron.
So on your screen now, you see the emission spectrum for hydrogen. And I want to pause on this for a second because it is hugely historically significant. In 1885, Johann Balmer figured out the pattern. By looking at the pattern of the wavelengths of the light emitted by passing electricity through hydrogen, Balmer figured it out. Now, I don't know if people in 1885 could have done it with anything more complicated than hydrogen, but I still think it's amazing. I don't know that I could do that myself, even knowing what the answer is. This was the first time that we imposed order on the chaos of the emission spectra for elements. And that's what's amazing, that looking at the color emitted by a gas can tell us about the internal structure of the gas. Physics is the art of measuring amazing things with counterintuitive tools. By looking at the color of things, we can know what those things are made of. So the Balmer series is interesting. You don't need to know this, but by putting in different values of n, we're able to get out different values of wavelength. And that's pretty amazing. If this were your high school class, they would probably ask this question and you would do it and it would be awesome and you would solve the problem, but we're not going to do it, which is so good. You could put in n equals 1, n equals 2, you could put in n equals 3 or n equals 4, and you would find exactly those wavelengths. And that's pretty amazing. As a smart AP Physics student, though, sometimes you have to be able to do this skill. What equation would they even use for that?
It would use C is equal to F lambda. And in order to get the frequency, you would just rearrange as frequency is C over lambda. And I remember from our previous lessons that C is equal to 3 times 10 to the 8th meters per second. And we would just plug in the given wavelengths from the previous slide to give us 4.57, 6.17, 6.91, and 7.55 times 10 to the 14th hertz.
10 to the 14 hertz, again, that's the order of the wavelength of visible light. Cool. So Bohr said that electrons only orbit in specific energy levels. The characteristics of those energy levels are related to the angular momentum of the electron, which means only certain values are allowed. So in this equation, another one that you don't need to memorize, it's outside the scope of the course. But what I want you to appreciate is that Bohr figured out that integer values of n, only 1, 2, 3, 4, etc., could fit this equation, that electron orbits were limited, and only those orbits were possible. When an electron moves from one orbit to another, it gains or loses energy exactly equal to the difference in energy between each level. Now, electrons gain or lose energy in the form of a photon. The energy of a photon, this we'll go into later, but the energy of a photon is related to some constant called Planck's constant times the frequency of that photon. E equals h times f. Well, the energy emitted or gained by an electron is equal to the difference in energy, energy final minus energy initial. Now, here's what that means on a picture. Again, it's worth 1,000 words. So if you look at the electron on the left side of your screen, it's about to drop to the next lowest energy level and emit a photon. So here's the transition and the emission happening together. The electron emits a photon and drops down. If you look at the electron on the right side of your screen, it absorbs a photon and goes up an energy level. So when a photon is absorbed, it promotes an electron to a higher energy level, but only certain wavelengths can be absorbed, only wavelengths that equal a possible energy difference. The list of those photon wavelengths, the ones that can't be absorbed, that's called the absorption spectrum. And I meant that. The ones that can't be absorbed are the absorption spectrum. Absorption spectra have missing lines. So here you see the different energy levels that are available in an atom. And remember, we said we were going to use those units called electron volts. Here is every possible absorption, every possible jump in energy level. Notice those are arrows going up because they represent absorptions. Photons that don't fit those jumps, those don't get absorbed. Only certain energies can be absorbed. And that's what makes up the absorption spectrum. And there is an absorption spectrum for that hypothetical element. Of course, if the element absorbs too much energy, something happens.
It flies away. It gets ejected. And so if you lose an electron, though, you become an ion, right? So if you lose an electron, you become positively charged. And so with an emission spectrum, an electron can drop to a lower energy state by getting rid of a photon, aka energy. You have to lose energy in order to drop to a lower energy state. And only certain wavelengths can be emitted, and the list of the wavelengths that can be emitted is called the emission spectrum. And these represent the different energy levels in an atom. So remember, on our absorption spectrum, all of our arrows pointed up. And in this case, these are my arrows pointing down because the electron is dropping in energy level. And in order to do so, that's the energy of the photon that's being emitted. And if you place those together, what do you get? You get the full emission spectrum of that particular atom. And just to give you a little bit of perspective on emission spectra, the absorption spectrum is at the top for the sun. And you notice that there's some missing pieces of the Roy G. Biv spectrum. And if you look at different elements that we've tested here on Earth and what their emission spectrum actually looks like, what it's known to look like, the missing pieces in the emission spectrum for the sun are all found in the elements hydrogen, helium, mercury, and uranium. All right, and we've got a little bit of guided practice for you to finish off. And we're going to answer two questions today. The first question is about the structure of nuclei, and the second is about absorption spectra. And we'll look at a series of questions about electron transitions between those discrete energy levels like we just got done talking about. And let's see our first question. Why do nuclei stay together despite the electric repulsion between the protons? And I think Mr. Mancino said it was a terrible name, an absolutely terrible name for this force that holds the nucleus together. So I don't think it's the first answer. Neutrons become polarized. What? We didn't talk about that. The second one says that the gravitational force is exerted on each proton due to the nucleon stronger than the net repulsive force. We didn't talk about gravitational force either. The net magnetic force exerted on each proton, I'm going to stop right there because we didn't talk about magnetic force either. But we did talk about the terrible name, the worst name for the force, and it's called the strong force that holds the nucleus together.
You know, we did get a second chance, a do-over. We got to name the second strongest force in nature. It's stronger than gravitation, stronger than magnetism, stronger than electricity. You know what we named the second strongest force in nature, Mr. Eaton? We named it the weak force.
What did we name it?
We named it the weak force. The second strongest force is named the weak force. What I'm saying is I appreciate really how difficult it is to learn.
All right. Here's our second question. An absorption spectrum observed for light traveling through interstellar gases appears as a broad spectrum of light with isolated dark lines at frequencies characteristic of the molecules of the gases. That's a lot of words for just saying we have an absorption spectrum. So which of the following is primarily responsible for the location of the dark absorption lines in the spectrum? So again, I know absorption lines have to do with absorbing energy to move up in an energy level. So I think the second answer choice is going to be the best answer for this.
So we have two transitions between energy levels. Which one shows emission? Well, emission is dropping from a higher energy level to a lower energy level and emitting a photon. Which of these emissions has a shorter wavelength? Well, shorter wavelength goes with more energy. Higher energy waves are towards the short end of the EM spectrum. So shorter wavelength has more energy. Which of these has a shorter wavelength? That's a trick question. They both have the same energy. Gotcha. Which of these has a shorter wavelength? Shorter wavelength goes with more energy. All right, I'm done asking about wavelength. Which of these has a lower frequency? Well, I remember that the energy of light is h times f, so energy goes with frequency. So less energy is less frequency. Finally, which of these transitions would emit photons with the same wavelength? I'll let you take a look at those. Wavelength is determined by the energy difference. So those two have the same energy difference. Quick question about color. Of these two, one is purple and one is red. Teachers, double check me on the wavelengths. The purple one and the red one, how would they be different? Well, I know in the Roy G. Biv spectrum, R comes first. It's lower energy. V comes last. V means purple. So purple has more energy than red. Bigger energy, bigger jump. Okay, a quick rundown of what we did today. The key takeaways are that protons and neutrons have component parts called quarks, that nuclei are dense and positives and held together by the aptly named strong force, that modern evidence challenged the classical model of the atom, and that electrons make transitions between discrete levels.
Can you describe evidence for light's particle nature and wave nature? Explain why nuclei stay together. Discuss the scale of gravitational, electrostatic, and nuclear force. And interpret an energy level diagram, and knowing when photons are absorbed or emitted, compare those wavelengths and compare the frequency and energy.
Okay, here it is, your quick AP Physics exam practice. Screenshot this question and we'll come back to it tomorrow at the beginning of the lesson. So there's an energy level diagram, electrons that are initially in the n=3 state. They undergo transitions and they emit photons. Can you sketch some arrows to indicate all the possible transitions that those n=3 electrons could make as they emit photons? Figure out which transition has the longest wavelength. Figure out the ionization energy of an atom in the n=1 state. How much energy would we give it to make this thing an ion? What would happen if 11 EV photons are shined on this atom? And what would happen if 14 EV photons are shined on the atom? So screenshot, take a look at that one tomorrow. So we know that not everybody has internet access and has access to a device. If you or someone you know has accessibility issues, needs a device, get in touch with the College Board now at cb.org/tech. There's a quick survey and they will reach out to you.
All right, thank you so much, everybody, for joining us, and we will see you tomorrow for our next AP Physics 2 lesson on modern physics.
Bye, everybody. It's been a blast.